Well, thank you very much, everyone. Good morning from British Columbia. My name is Jon Willis. And before I start my presentation, let me just give a quick couple of thank yous. First of all, to the SOC and LOC for putting together such a great conference this week and for the opportunity to join you guys today. And let me also thank my collaborators on this work. We've got Rebecca Canning, Emile Noorder, Ariane Trudeau, and Doug Renahan have all contributed a great deal to this work. So the title of my presentation is going to be the discovery and some of the implications of a massive mature galaxy cluster at a redshift of 2. So let me fire on into that. So the actual cluster we're talking about here, this is XLSSC 122 at a redshift of 1.98. And it's an X-ray selected galaxy cluster. And, you know, like many of these sources, it was discovered serendipitously. And to put it into context for you as to how faint and tenuous some of these detections are, this was originally detected as a 100 photon extended source in what was at the time called the XMM large-scale structure survey. I first looked at this cluster, it's embarrassing to say, about a decade ago. And that was when I started looking at infrared images of some of these faint extended sources that didn't show any optical emission. And my first contribution was really to work out the photometric redshifts of galaxies in the fields towards these sources. And in the field of XLSSC 122, we confirmed a photometric redshift spike at a redshift of 1.9. That kind of set the starting gun on a lot of follow-up efforts that I just want to mention a couple to you. The first was in 2014, Adam Mance used the Karma 30 gigahertz array to confirm a Sunyaev-Zeldovich decrement in this source. And that was important because that's a second independent confirmation that there's hot virialized gas in this cluster. So that, you know, gives you confidence that you're looking at a real collapsed structure. He then followed up on that by taking a much deeper 100 kilosecond XMM image on this galaxy cluster, confirming some, you know, really quite important physical parameters. So obviously the mass, about 6 times 10 to the 13 solar masses, but also the temperature and the metallicity of the X-ray emitting plasma. And what we got there was you got a temperature of about 5 keV, which actually shows a rather deep gravitational potential well. And in terms of the metallicity, well, that's the same metallicity that you typically see for low redshift clusters. And this sort of suite of observations, when you take them together, this is why we call this a mature galaxy cluster at a redshift of 2, because its physical properties are very similar in many senses to those which you see in local galaxy clusters. And it tells you that the physical processes that are helping to establish the physical character of galaxy clusters must be operating at, well, in this case, at redshifts greater than 2, okay? And then on the basis of all of that wonderful work, Rebecca Canning and I were able to obtain HST wide field camera 3 GRISM spectroscopy on this cluster, relatively deep spectroscopy, and we confirmed 37 members at a redshift of 1.98. So what I'm going to do now is I'm just going to take you through some of those HST observations that help characterize the cluster. Let me just make sure my slides are going to advance. There we go. And this is, first of all, this is the redshift histogram that we obtain. And essentially, the red bars indicate galaxies that we're pretty certain are members of the galaxy cluster of the redshift of 1.98. Green represents lower confidence members. Blue here, and this is an important color scheme we're going to use through these plots. These are galaxies of the redshift of 1.93 in what is essentially a completely unrelated foreground structure. The co-moving separation between these two peaks in redshift space is about 70 megaparsecs. And so this is not a local galaxy group or approximate filament. These are completely distinct objects in redshift space. And so we essentially ignore this blue peak in our subsequent analyses. And then this is just for those of you who aren't familiar with WFC3 GRISM spectra. These are just 2 example spectra of cluster members. The top panel is actually the BCG, and the bottom panel is a blue member. Pardon me. And what you can actually see here is it shows both the strength and the limitation of these WFC3 spectra. They're low resolution, but relatively high signal to noise ratio. So although we can get a redshift, it's not at high precision. It's around about 0.01 in redshift space is the precision you get here, okay? Then this is actually what happens when you put that member information onto the HST image of the cluster. So as we had before, red are our secure members and blue are these unrelated foreground objects. And then the black contours here show the XMM emission from that 100 kilosecond image. And for all intents and purposes, if you weren't specifically told this was a Z=2 cluster, you'd think that's just a classic low redshift established galaxy cluster. Okay, the important thing here is that I'll keep coming back to is that you're at a redshift of 2 and a look back time of about 10.4 gigayears. This is the color magnitude diagram of the galaxy cluster, and it's one of the notable points because there's not actually a great deal of explanation you have to give here. You can see a well-established red sequence and a very well-separated blue cloud, and immediately that tells you that the physical processes that lead to the establishment of the red sequence and also quenching so that you have a big separation between the blue cloud, they must be operating effectively at these redshifts and quite possibly beforehand. What it also indicates, a short point I'll just emphasize, you can see here the blue points representing the foreground structure are completely coincident with the red sequence of the galaxy cluster. And this really indicates why spectroscopic redshifts are critical in these kinds of situations, right? In photo-Zs at these redshifts, blending of proximate structures on the line of sight is a real issue. Now, fortuitously, these two filters in HST, F105 and F140, at the redshift of the galaxy cluster exactly span the 4,000 angstrom break. And so essentially the y-axis on this plot represents a relatively precise measurement of D4000, the 4,000 angstrom break index. And so using that information, I performed a very basic SED analysis just to convert that D4000 information into a weighted stellar age as a function of stellar mass. And this, as you can see, in a sense, these posterior, contours here, they represent essentially a transformation of this color magnitude diagram from color magnitude space into age stellar mass space. The horizontal line at the top here, that's the age of the universe at the redshift of 1.98. And you can see here that you're essentially getting the most massive galaxies appear to be really rather old. And then as you go down the red sequence members here, you're seeing greater variation in age. And that was so that's the story so far in a sense. And let me just kind of wrap up some of those results for you that I've already told you that when you look back to a redshift of 2, that's about 10.4 billion years ago. And so the universe at that age was about 3.3 billion years old. Yet when we look at this galaxy cluster, the member galaxies on the red sequence, now this is a big caveat, according to this preliminary analysis, they're between about 2.5 and 3 billion years old. And if you prefer that as a redshift, that corresponds to formation redshifts for those galaxies, somewhere between redshifts of 7 and 12, okay? Now, that's a point I'm going to come back to. The cluster itself, though, in its observed form, is probably no more than about 1 billion years old. Or perhaps a better way of saying that is that 1 billion years before the epoch of observation, this galaxy cluster was probably 10 times less massive than we observe it to be. And so what's really interesting in terms of observing such a well-established galaxy cluster, but at large look-back time, is just this last point here, that it raises the possibility that we can compare the galaxy's stellar ages within, to the mass accretion history of the cluster as a whole. And what I'm particularly interested in is whether we can learn at what cluster mass scale might be important in, establishing the major epochs of galaxy stellar assembly. So, of course, we published this in Nature, so what's likely to be wrong with all of this? Well, essentially, with just 2 colors, your SED model is very basic. You have to assume things like this metallicity of the stellar population and the dust obscuration. And we did our best to kind of bracket sensible values, but those are still big assumptions to make. And also, one obviously wants to deal with the cluster mass accretion history in a slightly more sophisticated manner than we had done originally. And of course, as one is often reminded, it's just one galaxy cluster. So let me kind of just, in this last slide, kind of give you a preview of our current work, and this is actually advertising Ariane Trudeau's talk on Thursday. So let me give you a couple of snippets to look forward to there. So here's the galaxy cluster again, with the members indicated, and essentially what Ariane has been working on is a much more sophisticated SED analysis of the members using all of the available photometry we have, ground-based and space-based. In this case, to do a much more sophisticated stellar population model, okay? And though it's a small panel here, these are basically the age posteriors that we get coming out here, going from about 0 to 3 gigayears. So these magenta circles represent what appear to be truly old systems, okay? But when you also look at other members on the red sequence, you find these orange intermediate age and slightly younger age stellar populations on the red sequence. And then also you see these cyan members, which are blue galaxies, and they are truly young star-forming galaxies. But what that allows one to do is to return to the color magnitude diagram and then actually add this kind of age classification onto the color magnitude diagram that really allows you for, in quite good detail, I would say, to look at age sequences along the cluster red sequence. What the final bit of advertising I just want to do is just to sort of show, this is some great work from Doug Renahan, who then went into the multi-dark 2 simulations and found approximately 500 XLSSC 122 progenitor clusters at a redshift of 2, right? He found about 500 halos that look like our galaxy cluster at a redshift of 2. And then he was able to form these histograms that kind of showed when those progenitors are accreting their mass and passing various thresholds. In this case, this gray histogram shows you the range of look-back times from redshift 2 when this cluster had assembled 10% of its mass. And what Ariane's going to kind of take you through on Thursday is essentially associating these age posteriors directly with the mass accretion history of the cluster. And so that can be my final comment, and thank you very much.